Welcome back. In this discussion, we're diving into Kirchhoff's laws, but we'll do so by first peeling back the layers of abstraction until we see the raw physics underneath. I want you to see that these laws are not just tools for solving circuits, they are the localized expression of global physical truths. Let's begin with the origin of Kirchhoff's current law and Kirchhoff's voltage law from Newtonian and atomic perspectives. Let's begin at the microscopic level. Every electric current is made up of moving charges, typically electrons and conductors. These charges follow Newton's second law. F is equal m times A. Now, in a conductor under steady-state DC conditions, the net force from the electric field causes a drift velocity in electrons. These electrons don't accelerate infinitely, they reach a terminal velocity due to collisions with the atomic lattice. That's resistance. Now imagine node A junction in a circuit where 3 or more wires meet. Electrons are flowing into and out of that junction. Here's the key idea. Charges are conserved. At the atomic level, this means electrons can't spontaneously vanish at a node. They can't accumulate in bulk without creating an electric field that counteracts further accumulation. Any net buildup of charge at a node would cause a Coulomb force that immediately adjusts the potential to prevent further accumulation. This stabilization happens very fast, on the order of picoseconds, so what we see macroscopically is no net charge accumulation. That's the physical origin of Kirchhoff's current law. The total current entering a node equals the total current leaving it. In symbols, summation of all the IK is equal to 0. This isn't an empirical guess. It is charge conservation applied to a spatial junction, and from a field theoretic view, it's a consequence of the continuity equation. Round rho over round t plus gradient of J is equal to 0, where rho is the charge density and J is the current density vector. In steady state, round rho over round t is equal to 0, so gradient of J become equal to 0. Integrating over a volume enclosing the node gives Kirchhoff's current law. So physically and mathematically, KCL expresses the impossibility of net charge imbalance at a node. Now let's turn to Kirchhoff's voltage law and again begin with fundamental physics. From Newton's second law, we know that a particle moving under a conservative force field will return to its original energy if it travels a closed loop. That's because work done over a closed path in a conservative field is 0. Now in electrostatics, the electric field E is conservative. This means the integral of E dl over closed loop become equal to 0. If you integrate the electric field around any closed path, you get 0. That's the physical root of Kirchhoff's voltage law. The sum of all voltage rises and drops around a closed loop is 0. But what is voltage? Voltage, or electric potential difference, is the work done per unit charge to move a charge between 2 points. So if a charge moves through a closed loop and comes back to its starting point, the net energy gained or lost must be 0, just like a hiker completing a loop trail returns to the same elevation. In circuit terms, summation all the Vk over a closed loop is equal to 0. This applies to batteries, which provide a voltage rise, resistors where energy is dissipated as heat, wires, which ideally have 0 potential drop. Even in a real circuit, the localized non-conservative fields inside a battery are balanced by conservative fields elsewhere, maintaining global conservation. Thus, KVL arises from the principle of energy conservation and the conservative nature of electrostatic fields. So why are these laws so important? Together, KCL and KVL allow us to write a complete set of equations to solve any linear circuit. They define the constraints imposed by physics. KCL constrains how current behaves at junctions. KVL constrains how voltage behaves in loops. They are the bookkeeping rules of electricity, and every circuit we ever build or measure must obey them. These two laws are the heart of nodal analysis and mesh analysis, the core methods we'll soon learn for solving complex networks. Let's cement our intuition with some physical analogies. KCL is like plumbing. Picture a sink with several pipes connected. If 2 liters per second flow in, then 2 liters per second must flow out. If not, water accumulates. In circuits, that would mean charge buildup, a capacitor effect not present in steady-state DC analysis. So KCL holds at every moment in DC circuits without capacitive storage. On the other hand, KVL is like hiking. Imagine you hike a loop trail. You gain elevation going up hills and lose elevation going down. When you finish the loop, your total elevation change is zero, just like the net voltage change in a closed circuit loop. So in summary, Kirchhoff's laws are not inventions, they are inevitable consequences of physical laws. KCL emerges from conservation of electric charge. KVL emerges from conservation of energy and the conservative nature of electrostatic fields. Together, they provide the mathematical structure to analyze and solve circuits. As we move forward, we will build our entire analytical framework on these two powerful laws. But never forget they are more than equations. They are nature's rules written in the language of electrons.